education and R&D. And some of you may have also participated in the webinar, Developing Leaders in Innovation. Following on this theme of innovation and cutting-edge technology, we now move on to our first keynote speech. The speech will be delivered by Professor Harry Shum, who is currently an adjunct professor at Tsinghua University. Professor Shum's work focuses on current trends in machine learning and artificial intelligence. As a computer scientist, Professor Shum is world-renowned for his research on computer vision and computer graphics, particularly the development of search engine Bing. Professor Shum is an international member of the National Academy of Engineering of the United States, an international member of the Royal Academy of Engineering in the UK, an IEEE Fellow, an ACM Fellow, and former Executive Vice President at Microsoft Artificial Intelligence and Research Group, focusing on current trends in machine learning and artificial intelligence. As a computer scientist, Professor Shum is well known for his research on computer vision and computer graphics. The theme for this keynote is From Deep Learning to Deep Understanding. We have allocated time for question and answer, so please keep those great comments and questions coming. As a courtesy, please remember to include your name and university in your message. Thank you, Professor Shum.
Thank you very much. Let me share my screen first. Can you see my screen? So may I get started?
Yes, we can see your screen. Thank you.
Okay, excellent. Thank you. Thank you very much for having me tonight or wherever you are around the world. I'm very happy to give this lecture at the Tsinghua Global Summer School. The title of my talk is From Deep Learning to Deep Understanding. So I have structured my talk really into two parts. The first part is more in the introduction of what's going on, what's happening in this field of AI and the deep learning. And the second part of my talk is really go deep into a particular example where I believe we should pursue if we actually want to move beyond just deep learning to really understand what's happening there. I just want to give you a little bit of background. It's hard for me to estimate, everyone's kind of a general knowledge in this field. So I would start slow in the first 10, 15 minutes. So, but probably you have heard about the DNN if you come to this lecture. This is probably the seminal paper people tend to believe the starting of this DNN revolution. It's actually a November 2012 speech magazine. Actually, a very nice paper by Jeff Hinton and colleagues from 4 different speech recognition groups around the world, including Microsoft Research in Redmond. And my former colleagues, Li Deng and others, collaborated with Jeff Hinton when he did his sabbatical at MSR. So it was a huge success to apply DNN to speech. Then very quickly, DNN was applied to computer vision and most recently in natural language processing. So I will also get to that. So it has been very, very exciting. So if I may summarize the great progress of AI in the last decades, especially with the progress of DNN, I would say I probably would use the following 3 sentences. The first thing is really the unreasonable effectiveness of data. With huge amount of data, and all of a sudden now we can actually learn a lot of interesting things. Of course, the breakthroughs in algorithms are also key. But let me emphasize, or maybe even overemphasize, the unreasonable effectiveness of big data. Now, I will use some numbers to justify my view here. Then, of course, is the unreasonable demand for more and more computing power. we're just more and more hungry about more computing power, which actually is going to cost us a lot of problems, if not a lot of money. But my talk today is actually probably going to be even more so on the third point, that is the unreasonable procrastination of general intelligence. With all the hype about the DNN, one could argue that we're not really that much closer to the general intelligence. So those are the three things I want to make sure that you get from my lecture today. Let me start with data. I use two examples here, and one is actually in computer vision, where I would represent the amount of data from the number of layers of the neural nets. Then I'm going to have the second example in natural language, where I'm going to use the number of parameters used in those humongous DNNs. This is a slide I borrowed from my former student, Dr. Jian Sang, and that was really after he and his team invented the ResNet. As I said, that DNN was really became popular probably around 2012, and when it was applied to speech recognition. Then Jeff and his students, realized this power and applied it to image nets, to computer vision. This is when AlexNet came out to just completely shock the world with the amazing result and the performance on the ImageNet data sets. AlexNet actually used 8 layers of deep neural nets, and at that time was unheard of. And very quickly, people realized that. So by 2014, VGG came out, and that actually used the 19 layers. Then later on, Google Nets used the 22 layers. But very quickly, that Microsoft research team in Beijing actually invented ResNet with 152 layers. Today, if you are doing anything in computer vision, you're probably using ResNet, and people nowadays don't even think about. And whatever problem they have in computer vision is started with probably a standard ResNet 50. But my point here is actually with 152 layers of the neural nets, and that's actually a huge amount of the data. It's just a huge amount of the data that you need to even train this level of deep neural nets. So that's in computer vision. And I should also say that by the time ResNet came out, and the classification the results were so good that they actually pretty much surpassed human performance. And the last couple of years, natural language is actually the new battleground for DNN, and people are just simply going crazy with bigger and bigger models. Only a couple of years ago, that when Elmo came out, people thought that's amazing. You can actually do this kind of work. And the BERT model was like huge, and with 340 million parameters. We were thinking about it. Gosh, why did you need that many parameters? You're probably overfitting somewhere. Then very quickly, GPT-2 came out with 1.5 billion. And only a couple of months ago, GPT-3 came out with 175 billion. And before GPT-3 could claim the world record, and a couple of weeks later, Google came out with G-Shard with 600 billion parameters. And you can imagine that this race is not going to stop, and they just continue to have bigger and bigger models. And of course, in order to train this kind of models, you actually need a huge computing power. And indeed, that has been the key to power all this kind of progress with DNN and AI recently. And by and large, and most of the computers today, follow, von Neumann architecture, where you actually have data and the program all together. This actually has the bottleneck at the cache level, because as you pass the data, from core to memory, and this is actually a bottleneck. Recently, a lot of people working on this new kind of architecture, including so-called neural computing, where you try to eliminate this monumental bottleneck of cache. But pretty much today, I would say, the most computers are still following von Neumann architecture. So the last several years, it has been amazing. If you look at the progress in the amount of the computing power, sometimes we say the special purpose computing, especially I would say the rise of GPU, TPU computing paradigm, and the GPU mostly from NVIDIA, and the TPU is really championed by Google. You can see that the number of teraflops that those systems can provide is just simply stunning. And I must point out that NVIDIA really led the wave and benefited tremendously as a company financially. For someone like me who has been in the field for over 30 years, just think about that. Another chip company go past Intel in terms of market cap is simply stunning. Good for NVIDIA. It just once again and it shows us that in our fields, in computing, you can never stop. You just have to keep going. I look forward to even more teraflops, in the coming years. So with all this kind of computing power, of course, it's never enough. So initially, you have all the CPU clouds, and you pack that to a GPU box. And then because with one simple box, you can train larger model with more data, and it's just easier for most researchers. But now people realize that even those big, powerful NVIDIA GPUs are not enough. Now we're moving on to those kind of GPU, TPU clouds. We have those big boxes again. So it's great that we continue to have that. Even in China, even today, there's big news that the AI chip company, the IPO. Again, it shows that the never-ending, unreasonable demands of more and more computing power. But I do want to point out that with all this kind of computing power, we actually pay for the price. This is a very nice paper coming out only 10 days ago on arXiv by some researchers from MIT and other places. It actually showed that there are computational limits for deep learning. And the deep learning has been designed and by the very definition that you actually have some problems. And it's just inherently expensive, and it just requires a huge amount of the data, to do anything interesting. There are some very interesting numbers from this paper I want to share with you. Again, it's a really brand new paper, only 10 days ago, coming out. Like the BERT model I mentioned to you a little bit earlier, like a few 100 million parameters. To train a BERT model, you actually need about $7,000. With the GPT-3 model, if you want to train a GPT-3 model with 175 billion parameters, you actually need $12 million US. Let me say it again, $12 million to train a model. So that's certainly not reachable, by most of us. A few rich companies can afford to do that. So that's it's actually a problem. And even more so, if you really want to get to like a human level, if you want to continue to push and the certain benchmarks, according to this paper, a very interesting number they actually called out, even with most conservative estimates for more computing power needed to achieve 5% of the target for ImageNet is actually going to be 10 power 5 more computing power needed. If you don't change the very formulation of DNN today, and you better pray for more computing power and coming to your way, and hopefully it's not going to be that expensive. So hopefully you get the point that in the last decades that the huge progress with DNN, a lot of good things already happened, and in addition to unbelievable algorithm breakthrough. It's really because of the huge amount of data and the huge amount of compute that pushed the entire field. But here comes the somewhat not very rosy reality. That is, despite all of that, I don't think we are that much closer to the real intelligence. We don't really exactly know what we actually learned. And for those things we kind of learned, it's actually difficult to explain. And some people now start to talk about that. Maybe we should go back to the good old fashioned of AI to really rethink about the knowledge, cognition, and the reasoning. So this is actually where I want to show you some examples. So hopefully to convince you. So my former colleague, Marco Ribeiro of Microsoft Research in Redmond, and he actually did a fantastic PhD thesis from University of Washington. The next couple of slides are directly lifted from him. So he studied something called explainable AI. He actually ran some deep learning models, and I believe it's either AlexNet or GoogleNet, for this example here. So what he wanted to do is actually to classify, a picture, to know whether this is a wolf or this is husky. Well, they look kind of similar, but they're really different. You better be careful. If you take a wolf to your house, you think it's a husky, then you might be in trouble. So he trained the model. It actually worked pretty well, by common standard. It turns out that he applied and only got one result wrong. So 5 of them he got right, and 1 got it wrong. But why? This one he didn't get it right? So he actually devised a model called LINE. It's kind of locally interpretable model agnostic explanation model. And it's actually very, very nice. And he, at a very high level, let me just explain to you that, what he realized is actually where this model, which pixels actually his model really used to classify whether this is a wolf or this is husky. So this is what he found. It turns out that for those pixels, he actually his model used to classify as wolf or husky. None of that, by human eyes, you probably would agree with me, none of them actually looks like wolf or husky. If you look at very closely, and you probably also realize that any of those picture where you use those pixels, they probably look like there's some snow on the ground. Then you say it's a wolf. For those pictures, you have no snow on the ground, and they look like they're huskies. So it turns out that deep neural net didn't learn anything, about wolf or husky, from at least in the human's point of view. And what they really learned, very likely, is the snow detector. So that's actually what's going on here. But that's in the computer vision. Let me show you some examples in natural language. And this is something called adversarial attack. And I'm showing you a couple of examples here. On the left, there's an article about the Super Bowl 50. And then there's a paragraph here. Then there's a question. Then the system is trying to answer. So the question is that, and so what is the name of the quarterback who was 38 in Super Bowl 33? And the answer is actually John Elway. Without this blue line, the system actually got it right. But with this blue line add on as the adversarial attack, and the system completely blew it and got it wrong. So now you see, how brittle the system really is. The right-hand side is another example, where there's a really interesting system called the text fooler. It's just by switching, a few the words, and you actually completely fool the system, and the system will really classify this whole thing, as a negative or positive, feeling here. So that's an example here. So I do want to show you, even more interesting example, with GPT. Now, I didn't have time to run GPT-3 examples, and nor I had enough money to run those GPT-3 models. But I do have some GPT-2 examples here to show you. So the GPT-2 actually, it's actually a very nice system, where you actually can answer some questions, or you can continue to write some text, given some previous text. Some actually looking pretty nice, and at least you think it's plausible. Like the first example here, say, well, two soldiers walked into a bar. Then the system can actually continue, say, in Mosul, and spend all of their money on drinks. That's kind of plausible. And but the second example is completely, just not right. And so yesterday I dropped my clothes off at the dry cleaner, and I have to pick up, where are my clothes? And the answer says at my mom's house. It's totally wrong. Similarly, the next example, you also got the wrong answer. So here comes, my hypothesis here. That is, I think that if you look at those examples, you probably agree that, the machine learning, deep learning has worked like a charm, but only to an approximation. So it really worked very well when you have a lot of data, a lot of compute, and you focus on some specific task. But it doesn't really have the general intelligence. It doesn't really have what some people call the robust AI. So to me, what's really exciting for the next decade, in the next 5 to 10 years in particular, I have some suggestions as well. But that's something that I want to, explain to you in the second part of my lecture today. So as I said that, more and more people start to really think about this issue of narrow AI versus robust AI. With all this deep learning, and what we have accomplished is mostly centered around a single task. With a huge amount of training data, especially with labeled data, it actually worked pretty well, but it's not very reliable. It sometimes works, sometimes it doesn't. And as I showed you, the wolf versus the husky, and there are many, many other examples. And of course, they are not really transferable to different settings, without extensive retraining. And one favorite example I like to use is AlphaGo. Obviously AlphaGo is unbelievable, right? AlphaGo beat the human champion. However, it's not clear, how we can apply AlphaGo algorithm to anything else. So AlphaGo has not solved the world peace yet, or the world's hunger yet. So there's still much more for us to pursue. That's why, people start to talk about robust AI or deep understanding. I highly recommend this book by Gary Marcus, Ernest Davis. It's called Rebooting AI. And also, Gary recently wrote a very long article called The Next Decade of AI. And I highly recommend you to read that article as well. Well, he really argued that we should go back to good old-fashioned of AI to really think about those difficult problems of common sense, knowledge, cognition. And we want to build the robust AI so that we can count on those AI to apply to a wide range of the problems systematically and reliably. And we can synthesize knowledge from various sources such that the AI can reason. And of course, just like humans, the AI can actually transfer what it learns from one context to another with probably few-shot learning or zero-shot learning sometimes. So my own thinking is that the result of ML should not be just a set of classifiers, one for each task. Even though it works really, really well, in most cases by now. Instead, I think a robust AI agent should be able to continue to learn skills and knowledge, just like humans, by practicing. Sometimes we call this in reinforcement learning, or by exploring. And if you have all those samples there, and they can be supervised, and if you don't have those labels there, you probably do the unsupervised. I have thought about this very exciting field, and I thought there are 3 very interesting directions I personally would like to pursue, probably with my students. The first area, is, in my opinion, is really building large-scale simulators. I mentioned about AlphaGo and all those gaming stuff there, but the autonomous driving is probably where we need to really build large-scale simulators. The second interesting area, in my opinion, is really go back to the basics of machine learning. And why do we have this kind of really expensive deep learning algorithms, just like this MIT paper I mentioned a little earlier? Now we see the computational limits of those the deep learning algorithms. Can we do better? And a lot of people are already looking at that. I particularly like one line of work, championed by Professor Yima at Berkeley. It's really go back to the optimization function, rethink about this problem. But I don't have time to get into those two very exciting areas today. And instead, I'm going to use an example to talk about the third area of my favorite. It's really about hybrid neural symbolic model for robust AI, and using an example in natural language processing, especially in conversational AI, to convince you that this is the right way to go. So this is actually, in my opinion, a very beautiful piece of work by my former colleagues in Microsoft Research in Redmond. So this is, as I said, is an example of conversational AI. They published this book, this paper, almost exactly 4 weeks ago. The paper is called, the system they built is called the Soloist. What they do is building task bots at the scale using a pre-trained, grounded text generator. It sounds a bit mouthful, but I will get there and I will explain to you what exactly they do. So basically, they have trained an end-to-end neural model with symbolic constraints. And they do grounded text generation. By that, I really mean the results really make sense. And they actually did fine-tuning and using few-shot learning, which I'm also going to skip because of the lack of time. So let me make sure that you understand what we are trying to do here and in this paper. So this is actually a multi-domain dialogue session. So this is what you will get if you actually talk to some kind of conversational agent or task bot or chat bot, something like that. So this is an example of completing a multi-domain task. So produced by this paper and produced by this method they call the GTG, grounded text generation. So the user starts the conversation by asking for a recommendation of a museum in the center of the town. So the system identifies the user request and provides a recommendation based on the search results from an attraction database. Then the user wants to book a table in a restaurant in the same area. So GTG, the system from MSR, understands that the same area really refers to the center of town. So this is because they actually have this capability of co-referencing. Then they identifies a proper entity from the restaurant booking database and successfully makes the reservation. So this is basically a diagram for a typical dialogue system. This is the classic architecture of modular dialogue system. So a typical task bot, consists of 4 things. The first is actually a language understanding module that identifies user intents and extracts associated information from the user input. The second part is DST, or dialogue state tracking. That infers the dialogue belief states, so what the user really wants, and queries the data set to obtain the database state, such as how many entities that will match the user goal, so that you can update the dialogue state. The third piece is actually dialogue policy, that it will select the next action based on the dialogue state. And finally, the fourth module is the language generation that will convert the action into a natural language response. So the language understanding and the generation modules can be implemented using language models such as BERT for LU and the GPT for LG. So what's unique here is really the dialogue manager, which actually consists of DST and the policy. So traditionally, in order to build this kind of modular system, it's actually really, really hard, mostly by manual, and it's very brittle. And if you don't cover those cases, then they typically the user will get lost when using this system. So here is really how we have been really thinking about this whole thing, and to build a more robust AI system, by really using the latest machine learning techniques, try to build an end-to-end system yet, and make sure that we actually have the cognitive model there for the DST, and we will leverage the knowledge, the symbolic representation from all those databases there. And ideally, we can also do the reasoning, with common sense. This is, we want to design. This is how we want to do it, and we believe that we should do a hybrid model using, both the neural approach and leveraging the symbolic representation as well. But doing that is actually hard, and the implementing the knowledge and the reasoning with modern machine learning techniques, DNN, is actually not easy. Certainly, there is a huge advantage there doing deep learning for knowledge representation and dialogue state tracking. So this is actually a system we have built, and let me walk you through and what's really happening here. So it shows how we formulate this new modular dialogue system as an autoregressive model. So the modular system can be viewed as a data generation pipeline consisting of 4 different units. That is the NLU, DST, policy generation, and NLG. They actually process data in sequence, where the output of a previous module is the input of the next module. So if we implement each module using a transformer-based neural network, then we allow all those neural networks to share the parameters. And then the whole pipeline can be implemented using a transformer module. That is exactly what we call GTG, grounded text generation. I explained to you why we say that. So since the GTG actually plays different roles in the process of generating a response, we use the multitask learning to pre-train GTG on large amount of heterogeneous data. So there are really 3 tasks here. So we use this multitask training. So the task 1 is the belief state prediction, trained on the dialogue history, belief state pairs. And the task 2 is really the core here, that is grounded response generation and trained on inputs, output pairs, whereas the input is the concatenation of dialogue history, belief state, and the database state, and output is the lexicalized response. Finally, the task 3, we use the contrastive learning. So we view each dialogue turn in training data as a positive example. Then we sample a few negative examples by placing one of the items with a randomly sampled item. And that's how we actually do it. And the GTG learned to give the higher scores to a positive example and the lower scores to the negative example. I don't need to bother you with more, mathematics here, but you just need to believe me that, you write down all those equations and, you pretty much can solve that. And eventually you get this transformer-based GTG model. So I do want to make a few comments about the GPT versus GTG, right? So the GPT is this fancy model. You probably have heard, you probably have read the papers. If you haven't seen the GPT-3 paper, which just came out a couple of months ago, and you are welcome to flip through it. And it's really not much huge insight there. The results are very impressive, but you get the basic idea. Probably GPT-2 paper is probably more informing. In any case, GPT, whether it's GPT-2 or GPT-3, they learn to understand and generate natural language. So they pre-trained on raw text, and they fine-tuned it to perform specific language understanding and generation tasks. So they basically learn how to talk like a human, learn from all the raw text. But what we are doing here in this project is very different. So GTG is actually learn to predict the dialogue states and generate a grounded response for task completion. So what we are learning here is actually what to say to get the job done. So that's the difference. So here's an example that's basically showing that GPT-2 with this kind of a dialogue history, GPT-2 will generate something that's completely useless. And the GTG, what we have shown here is that not only we can get this delexicalized response, and we can also plug in the database, get the grounded the results. That's probably what the users really want anyway. So I'm quickly going to walk you through how we actually evaluate our system, and to show our results are really, really good. So we evaluate on 2 public benchmarks, and it's important to understand how to evaluate this kind of systems. There are really a few dimensions here, and one is inform measures whether a bot provides a correct entity that matches the user goal. Second is actually the success measures, whether a bot also answers or requests the information. Then there's this traditional blue score, and in natural language that really measures the fluency, whether it talks like a human. And then we'll put together with a combined score, and we'll see how we actually get to compare with others. So we have this data set used for the pre-training, and here's the result. So it's really worked out really, really well, and compared with the state of the art. So most of the previous systems were not really the grounded, and except this DSTC8 winner, they kind of partially grounded. But in any case, that our results significantly better by using this hybrid model that is really the end-to-end system, by adding this grounded generation, symbolic constraint, so to speak. And there's another example we actually also used, and different kind of evaluation there, and looked at the 50 dialogues per task in few-shot learning. Similarly, we are significantly better than others. So it gives us a significant confidence that this might be the right direction to go if we actually want to move beyond deep learning to deep understanding. So this is pretty much what I want to talk to you today, and hopefully I have given you some background about what has been happening in the last decades in AI, in deep learning. While exciting, it's time for us to move on, especially for the next 5 to 10 years. I believe that it's going to be golden era for us to pursue hybrid neurosymbolic models, coupled with knowledge-driven cognitive model-based. We might have a chance to really have a shot at a robust AI, or at least we'll make some significant progress there. Thank you very much for your attention. I want to acknowledge some of my former colleagues for their contribution to this presentation. Thank you.
Well, thank you, Professor Shum, for those fascinating insights and into deep learning and deep understanding. Our chat function has been very engaged and active, and I can see some really fascinating comments and interactions, and here are just a selection. Dink Muhammad from KAIST has asked, how do we design reinforcement learning not to be very focused on one specific task?
Yeah, I haven't really touched on the reinforcement learning much, in this presentation. I did hint that one of the three areas I personally would like to pursue and towards deep understanding is actually on simulators. To me, the real secret sauce for reinforcement learning and including deep reinforcement learning, such as AlphaGo system, is really the ability to build high quality simulators. And as you try to learn with reinforcement learning, which is basically by practicing, and you want to explore with this action what you actually get. To me, I think it might be a little bit of brute force. It might be a little bit too engineering focused. But I genuinely believe that if we are willing to spend $12 million to train a GPT-3 model, I think we should spend more money to build high quality simulators.
Okay, thank you for that response. The next question comes from Rachel Tsai, and she's asked, do you think deep learning technology can continue to develop or is coming up to a dead end, considering the skyrocketing environmental costs and dishonest developers?
Yeah, this is a fascinating question, and I wouldn't bet against it. I think there's still a long way to go, for deep learning to continue to make big progress. But I did caution you, from this lecture that it's really the unreasonable effectiveness of big data, and also it's just unbelievable progress of big computes that have pushed us. But I'm also very encouraged by the lot of good work in recent years, going back to the core of deep learning itself and what exactly we are learning. That's actually the second topic that I mentioned that I believe the next 5 to 10 years will be very, very exciting. That is really deep understanding of deep learning itself. I wish I had the time to talk a little bit about Professor Ima's work from Berkeley. Actually, in a different conference tomorrow, he's going to give a keynote, probably share some of his stuff there. His paper also recently published on Archive about a month ago. It's really going back to what you try to optimize, and what is the optimization function there. And maybe I'll give you a very high level answer there is that think about that over the years that what we have done for clustering, for classification, for learning, and there is an objective function behind everything. Now if we want to understand what's really going on, maybe we should just revisit the objective.
Sure. Thank you for that response. I've been allowed to extend this session by 5 minutes because all our participants would love to keep asking questions. So I do have one final question. I'm interested in how the pandemic is affecting the development of AI. For example, how is it disrupting research? Or, for example, are there any emerging AI-specific innovations that might alleviate the pandemic?
Yeah, that's an excellent question. That I wish the AI and the machine learning could have done more to fight the pandemic. Of course, there's almost in every aspect that machine learning has been applied. Just as a practitioner, I wish we could have done more. I have seen a lot of very nice work and from scientific research community to really help different people how to fight this pandemic. In the research field alone, I must call out the excellent work, by Allen Institute of AI and also by Microsoft Research in preparing and helping with this large body of research literature and anything related to fighting pandemic, not only just in computer science, but more and more in health. So it's really excellent work, and every day they actually update this huge database, making sure that all kind of researchers can access to this kind of information in a timely manner. I really appreciate this kind of work, and I think it's something that we together as a research community should do.
Well, thank you so much, Professor Shum. I think that has been such a productive and amazing session, and I would like to thank you for your contribution to this